All right, so let's go. Okay. All right, so last week we looked at how we do a change of coordinates. All right, come on, settle down, please. How we do a change of coordinates in double integrals, and this is a bit different to a change of variable with integrals of function of a single variable, because well, for our purposes, they'll be motivated by the region we're integrating over, not motivated by the function we're trying to integrate. So when we do a double integral, we either have to come up with a suitable mapping, that will be sort of explained in the question, or we use polar coordinates if the region in the xy plane we're integrating over has some sort of circular symmetry. We can do the same thing with triple integrals, however coming up with a new coordinate system is very tricky business, something that comes with years of practice. So we're going to concentrate on two types of coordinate systems in triple integrals, and they were the cylindrical coordinate systems, which are basically a basic 3D extension of polar coordinates. And so in cylindrical coordinates you have r, theta and z, so r and theta act like your polar coordinates just like normal, and z acts as it always does. And then another one which is spherical coordinates, which involves two angles. And we use the order r, theta, phi, where r and theta, rho, theta, phi. Theta is like the polar angle. Rho is the distance from the origin, so that defines spheres. And phi is the angle measured from the positive z-axis going down, right? And in some textbooks, they will reverse the order for spherical. So some textbooks might use r, phi, theta. So if you're looking in a textbook and they use different order, right, then some things will be backwards. Of course, the final answer will be the same. But we use the notation rho, theta, phi. So because then theta's in the same spot that we're used to, in the second spot. All right? Now, I went through this this example. Right, well, basically how to find the volume of this ice cream cone. So we have a cone and a spherical cap, so it's best described by spherical coordinates because the coordinate planes in spherical coordinates are spheres, planes and cones. Right, so cones are constant phi. Imagine dropping the angle from the positive z-axis and then rotating it around, that defines a cone. Right? Let's have a look at this one. Now, if I asked you, what's the formula for the volume of a cone, basically, with a circular base? Well, you've probably come across the formula that it's a third pi r squared h, where r is the radius of the bottom of the cone and the h is its height. Right? Again, prove it. Right? How could we prove it? Remember I said that a lot of the time with integrals can be used to actually calculate these volumes from first principles. So to work out, let's say we've got a cone that's got some height h, so z runs from 0 to h, and I've chosen the coordinate system, so the centre's at the origin. The first thing I need to do is to describe its surface. I need an equation to describe its surface. And it turns out that the surface of a cone can be represented by x squared, the equation x squared plus y squared equals a squared times 1 minus z on h all squared. Right? This makes sense. If you take a slice at a particular h, so take a level curve, so for example at the bottom, at the slice z equals 0, that should be a circle of radius a, right? And when you plug in z equals 0, you get x squared plus y squared equals a squared. Right? Take a slice all up, as you slice further up, the circles just get smaller and smaller and smaller, don't they? Until you're up the top, where if you sliced right at the top, you get a point, basically a circle of radius 0. So when z equals h, you can say you get x squared plus y squared equals 0, right? And then all the circles in between. If I wanted to do this in Cartesian coordinates, the first thing I'd have to do is I'd have to solve this for z, right? Which isn't too bad. You will bring in a nasty square root though, right? And then you've got plus minus. Obviously we want the positive bit of it, so we could take the positive square root. But doing that in Cartesian coordinates would be a lot of work, right? It's actually easier because its level curves are circles, and we have the cylindrical coordinate system where we basically got cylinders. It's best to use cylindrical coordinates in this case. Right? And that's also illustrated by the presence of the x squared plus y squared, because you know in cylindrical x squared plus y squared is r squared. Right? So if I'm going to use in cylindrical coordinates, I could describe this surface as r basically goes from 0 to, you replace x squared plus y squared with r squared. So r basically goes from 0 to the square root of this. I take the positive square root because I'm calculating a volume here. Everything's going to be positive. If it turned out my answer was negative, all that means is I took the wrong square root and I just dropped the minus sign. But you'd have r going from 0 to this bit, the square root of this bit. And I want to sweep out the whole thing. So theta, which is your angle in the xy plane measured from the positive x-axis going anti-clockwise, goes from 0 to 2 pi. And z in this case just goes from 0 to h. Right? So it's much nicer to describe this in terms of in cylindrical coordinates. Then the volume, because I want a volume, I'm doing a triple integral of the function 1, right, to give me the volume of this thing, times the Jacobian correction in cylindrical coordinates, which is just r. So remember, that's on the formula sheet. You're never going to have to rederive that. Right? And as I explained, don't muck with the order. Always do a dr d theta dz. Right? So that's basically just this one. And again, note in the lecture notes we use xi for z, but I hate writing xi. Xi and z are, of course, they're the same bloody thing. Right? And z's easier to write. So, I mean, technically this should be dr d theta dxi, but I can't be bothered writing xi all the time, so I just use z. Right? Z acts as normal. Right? So then I've just got to integrate this. No nasty square roots and things like that. R goes from 0 to a times the square root, a times 1 minus z on h, theta 0 to 2 pi, z 0 to h. You just plug everything in, do the algebra, and you'll get down to the formula as you see fit. Right? Right, so usually the hardest part with these is figuring out what are your limits on r. So for cylindrical, you've got to figure out what are your new limits in terms of r, theta, and z. And in spherical, you've got to figure out your new limits in rho, theta, and phi. Right? But most of the time, if I want you to do one of these in spherical or cylindrical coordinates, I will tell you. Right? I'll say, perform the following triple integral by converting to cylindrical or spherical coordinates. Right? So I actually tell you that's what you need to do. Okay? Alrighty, let's move on. So do have a work through that example, and again make sure you understand how you map points to point, how the coordinate planes work, right, and what they look like. All right. Now the next thing we're going to do is we're going to go back to what we did several weeks ago, was looking at representing curves in 2D and lines in 3D as vector-valued functions. Because we can do integrals on those as well in parametric form as opposed to Cartesian form. You might remember that one of the reasons we use vector representations of functions is they make certain things easier. The classic one is the circle. You can't describe the whole circle as a function y equals f of x. You can describe the top half as the positive square root of a squared minus x squared, and the bottom is minus the square root of a squared, but you can't describe the whole thing. Whereas parametrically, if you let x equal a cos t and y equal a sin t, or the other way around, right, a sin and a cos, doesn't matter which way order you do it in, right, it makes life much easier. You can describe the whole thing in one hit. Right? Now we can actually do integrals with these parametric functions as well, and we can find things like we can do lengths of curve, path integrals, we can calculate surface areas, and there's a fourth thing, we can do surface integrals, but we're not going to do those. We don't have the time to do them properly, and because they lead into something called vector fields, which we've had to drop from this unit. It's not covered anymore. So we're just going to stop at surface areas. Right? Now, recall that when we looked at integrals involving Riemann sums, right, so, one of the formulas we derived, I could find the length of a curve. If I've got a curve y equals f of x, I can calculate its exact length via this formula, right? So I've just got to find the derivative, plug it in, and do it, right? And this will give me the length of the curve, provided, of course, I can find the integral. What if the curve, though, is described parametrically, and it's not possible to describe the whole thing as a function y equals f of x, right? This formula can't handle that. And what if we've got a curve in 3 dimensions, you know, like a helix or something? Obviously, this one can't handle that either. This is a strictly 2D construct, right? So we need to be able to find these things like lengths of curves and stuff for functions that we represent as vector-valued functions, right? Right. So, for example, how could, if you've got, say, a climber scaling the side of a mountain, how could you find the actual length, right? Provided you can find a suitable parametric representation of that path, we can find its length by doing an integral, right? And with integrals, you know, we've seen how useful integrals are. We can actually find the surface area of a mountain as well and things like that, all by doing a surface integral, right? Again, we're only going to look at a specific case, and that'll be next week. Right, so knowledge of this requires methods of path integrals and surface integrals. Path integrals are also sometimes called just line integrals. Same bloody thing, line or path, right? I prefer the term path integral, but some textbooks might call them line integrals. Again, the hardest part, well, not the hardest part, but the point here is, first thing to do is come up with a suitable parameterization that's convenient in what I mean by convenient is lets me do the integral as easily as possible, right? Remember when we did vector-valued functions, a vector representation of a function is not unique, right? And sometimes you can be clever with how you choose the parameterization, right? And to make life easier. And particularly with integrals, we always want to try and make life easier. Right? Right, so let's go back and review what we did for paths first. Right? So given some curve in 2D or 3, or in fact any dimension, but we're going to stick with just 2 and 3, we introduce a new variable. We usually use the letter t. Imagine t varies from A to b. And then x and y, in 2 dimensions, either x and y are both functions of t, or in 3 dimensions, x, y, and z are both functions of t. And so these describe a vector, and if I trace, as t varies, what the head of that vector, the curve the head of that vector traces out is the curve I'm looking for. Right? And then we have some other notation. We have the position vector and velocity vector. We often use those terms interchangeably. Right? And note we use dot notation here because it is a derivative with respect to time, so we're allowed to use dot notation here. Right, and recall that this is the parametric form or the parametric representation of curve. And basically what we're doing is, you imagine as t varies, I've got this vector r of t. If I follow what the head of that thing's doing, right, that it traces out some curve. That's the curve I'm trying to represent parametrically. And its derivative, or velocity, which was sometimes called the velocity vector, basically the derivative of the position vector, is a vector that's tangent to the curve at a particular point t. Right? Now, first, so we're going to have to be able to come up with suitable parameterization. So let's have a look at a simple example first. Let's say we've got basically a straight line that starts at the point 1 and 2 and ends at the point 3 and 6. And I want to find a parametric representation of this curve. The easiest way to do this is force it to work easily. Right? So one way we could do this, basically what I've got is a straight line, and for some reason I don't want to represent this as y equals ax plus b, I want to represent this parametrically. Right? So basically I've got a straight line that goes from the point 1, 2, and ends at the point. So to make life easy, let's say I make it so the start point corresponds to t equals 0 and the end point corresponds to t equals 1. Remember, the parameterization is not unique. Let's make life easy. Right? 0 and 1. If we're going to do integrals on this thing, having limits of 0 and 1 is always handy. Right? Now, I can think of this, I can actually construct this very straightforwardly. if I do this, right, if I imagine that it's basically for a straight line, start point plus t times end point minus start point, this will work and do it for me. And the reason is, well, when t equals 0, I want to be at the start point, don't I? So, of course, when t equals 0, I'm at the point 1, 2. Done. When t equals 1, I want to be at the end point, right? So if I plug t equals 1, the vector 1, 2 bits cancel, leaving me the vector 3, 6. Right? So I'm at the end point. Right? So this is the simplest vector value function that will do this for me. And then you just clean this up. Right? So it shouldn't, you do 3, that's 1 plus, I usually write these as a single vector. And that will do it for me. Right, because when t equals 0, I'm at the point 1, 2, and when t equals 1, I'm at the point 3, 6, done. Right? So I can make this work for me and make life easy. Right? And that's basically what I'm explaining here. Right? So we can choose any interval of t I want. I mean, you could have t going from minus 47 to 36, but why the hell would you do that? Right? Make it easy. 0 to 1 is always nice, right? Especially if we're going to do integrals on these things. Right? And that's basically explaining how I get around it. Right? And so that's a suitable parametric representation. Right? Or you can do it the way I've just done it, like force it to work. Now, important thing to note is, especially when you're following along with textbooks or you look for some problems on Google and stuff like that, when we're doing integrals with vector valued functions, we often switch notations, right, between column vectors and row vectors. Right? So those of you doing 1012 will already be familiar with this, writing things as either column vectors or row vectors. So you either write it, I much prefer as a row. Right? I much prefer row notation than column notation with matrix brackets, but they're totally equivalent, of course. Right? Just depends what you're doing and which book you look in. Right? So we often switch between representing them as 2 times 1 matrices or vectors in the usual sense. Right? Just depends on the book and the person teaching it, basically. Right? Now, this simple example highlights several important points, because not only do we have to find a vector representation of this thing, we are going to be doing calculus with it, right? So there's a couple of things we need to do beforehand. So a parametric form is obviously a vector valued function. If it's a 2D curve, it has 2 components. If it's a 3D curve, it has 3 components. And again, if you want to go higher dimensions, you can, but we won't do that because you can't really visualize it. You need to specify where the curve starts and ends, right? So, because if I want to say calculate the length of a curve, I need to know the length from where to where, right? So you do need an interval of t, right? So in the previous one I had t going from 0 to 1, right? And again, usually we make this so t equals a is where it starts, t equals b is where it ends. If you come up with a parameterization yourself, you're free to choose those. Make it as easy as possible. Right? In the long run, it won't matter. Say if you've got a circle, right? If you've got to parameterize a circle, if you use cos and sine, then it starts at, let's say it's a circle of radius 1. Actually, I think we're about to do that example. I'll talk about that in a sec. Right? Right, so specifying t, we make a choice, and this is, again, illustrates the fact that parameterization is not unique. Right, again, let's have a look at the circle, right, the simple case. Now, one way we could parameterize this is basically what I call a brute force approach, right? Solve it for y in terms of x. Of course, this one you get 2 pieces. Let x equal t, then y is your function of x, which becomes a function of t. The problem with this one is this requires 2 separate parameterizations. I could have a parameterization for the top bit and a parameterization for the bottom bit. And for some unknown reason, I've used x as 1 minus t. I have no idea why. Right? Oh, the particle moves around the circle once, starting and ending at x equals 1, y equals 0. So when t equals 0, I want it to be at 1, 0, and there's t, I want it to trace around and come back. Now, I could do it that way, but then if I'm going to be doing integral, remember this is not unique. Right?
But if I'm then going to do integrals on this, square roots, 2 pieces, oh, the hell with that, right? There's got to be a better way. And of course we know with circles there is. Much easier to let, say, x equal cos of t and y equals sine of t, because this will do everything for me in one hit. Notice that when t equals 0, you're at the point 1, 0, exactly where I wanted it to start. If the question said I wanted to start at 0, 1, you could do that 2 ways. You could keep that parameterization but then have t going from pi on 2 to 2 pi plus pi on 2. You could do it that way. Or you could swap the cos and sine around. Right? If you have x equals sine and y equals cos, then t goes from 0 to 2 pi. It just starts at a different spot, but traces around the same curve. Again, it's not unique. Right? So there are 2 ways we can do this. Right? You either brute force it, or I try doing this somehow. The somehow is the hard part. Right? Now, of course, we know the reason this works, the reason I can parameterize it this way is because if I let x equal cos of t, y equals sine of t, I know that x squared plus y squared is guaranteed to be 1, don't I? Because sine squared plus cos squared always equals 1. That's why this works, right? And in fact, in old textbooks, the trig functions are called circular functions because we use them to describe frickin' circles, right? That's why we call them that, right? Anyway. But if you can't do that, you just brute force it, right? So the content, which one you do will depend on the question, depend on the function you're trying to parameterize, right? But you either brute force it, solve it for y in terms of x, and just let x equal t, y becomes f of t, right? Or if you've got an implicit equation, so something like, yeah, well, let's say you had x squared times y squared equals 1, and you wanted to parameterize that curve. Right? You try and solve it for y. If it has several pieces, you need several parameterizations, right? Just like the previous one showed. But if you can make it, or you can force the trig identity to work for you. If you can write it as something of x all squared plus something of y all squared equals 1, you can force this trig parameterization to work. Right? So at the moment, for example, we're just doing it by saying, well, you know, if you've got that, right, the reason this works is I know that this is always true. Right? So I want to make that look like that. Right? And of course it already does. Right? If you let x equals sine and y equals cos, it will of course the other way around. You could do it. What if you had, though, I don't know, that, and you wanted to parameterize that curve? Right, now you could let x equal t and solve that for y. You know, you got a sixth of the 6th root of something to the power of 6. You got to think the next step is we're going to have to integrate this rubbish. You don't want to integrate that, right? The key is think of it, can I write this as something squared plus something squared? And hopefully without too much thought. If you wrote it like that, which is of course the same thing, well then a parameterization that may work or in other words, right? That will work. You might not be able to do the integral, but it might. Right? So we try and make the fundamental trig property work for us if we can. Right? Because then when we're integrating, this is just going to be leading hopefully to just simple-ish integrals involving sine and cos, which hopefully now we can handle because we've done lots of cases of them. Right? Right, so we either do that, but if that's not obvious, then we just brute force it. Right? Now, I've got some examples here. Let's find a parametric form for a circle of radius 3 centred at the point x equals 3, y equals minus 2. Now, I know that that has this equation, right? X minus 3 all squared plus y minus 2 all squared equals 9, right? So I can force this to work, right? Because I can imagine it as, you know, if you divide through by 9 and whack it all in, it doesn't matter how you do it, but you can force this parameterisation to work. So a suitable parameterisation is that. And I've put the sine on the x and the cos on the y because, well, no, I didn't say, right? But this, the way I've put the sine and the cos here, that means it starts at that point and travels anti-clockwise. If you swap the sine and the cos around, all it means is it starts at a different point, right? But it follows the same path. What about this one? Right, and this is an ellipse. 9x squared plus 25y squared equals 225. So basically football. Right, so if I can write that as something all squared plus something else all squared equals 1, and those two somethings only involve either x or y, not together, I could make it work. Right, so if I play around with this and I write it like this, that means, well, if I let x on 5 be sine and y on 3 be cos, or the other way around, again, it doesn't matter, that parameterisation will work. Right? So a suitable parameterisation of this one is that, which will be much nicer to work with than having square roots and things like that. This doesn't always work though. So this one, xy equals 4, not much you can do with that. Right? There's certainly, I can't think of that as something involving x all squared plus something involving y all squared equals 1. Not going to happen. Right? So when it doesn't happen, you brute force it. Right? And the easiest way is to solve it for y in terms of x and pick the simplest one. Right? X is t, y equals 4 on t. We'll do it. Right? Not a particularly helpful parameterisation, but it'll do what we need it to do. Right? Right, and there's another one, right? So sometimes you can be a little bit clever. So here I could let x equal t, and then y is just t minus 2 on t minus 4, or I could maybe let x equal t plus 2, so y is a bit nicer. It's not unique, so it doesn't really matter. It all depends what we're doing with it in the next step, right? Which what we're going to be doing is integrating with these things. Okay. All right. Let's move on, actually do something with it. All right? Now, the following theorem explains how I can use the parametric form of a curve in any dimension. We're going to stick with 2 and 3, but in technically any dimension that I can suitably parameterise by an n-dimensional vector, like so. It turns out that the length of the curve is given by the norm of the derivative of the position vector. Right? Or, in other words, the length of the velocity vector, or the speed vector, we could also think of it that way. Right? So it's just the norm of, or length of the velocity vector, or the derivative of the position vector. Right? So as long as I've got a suitable parameterisation, so this becomes an integral in terms of t. Right? And I've parameterised in such a way that t goes from a to b, so the integral goes from a to b. Right? And we're just going to stick with 2 dimensions and 3 dimensions. Right, but how does this compare to the formula we've already got? Right? Now, of course, if you've got one that can be done both ways, it shouldn't matter, and of course it won't. It won't matter. Let's say we've got a function y equals f of x, right? And it turns out the only way to parameterise it is brute force it. Right? You let x equal t, y becomes f of t. Right? So in vector notation, the way I would choose my parameterisation is my position vector would be just t and f of t. And I plug that into this formula. I need the square root of the derivative of the first bit squared plus the derivative, basically the derivative of this, which is 1 df dt, and its length. So the square root of 1 squared plus df dt all squared. And of course, same damn thing. Remember, this is a definite integral, so this one's just integrating with respect to t, that's with respect to x. Who gives a crap? Right? It gives the same answer. Right? The advantage of this one, though, is this will allow us to handle functions that I can't write, handle curves that I can't write as functions, or is not convenient to think of them as as explicit functions y equals f of x. And this now allows me to figure out the length of curves in 3 dimensions, not just 2. Right? So I'm no longer stuck in 2 dimensions. Right, for example, one of the vector valued curves we looked at was a helix. right? So remember, this is one that sort of spirals around the outside of a cylinder, right? And we can see that, well, you can see that if x is cos t, y equals sine, we see x squared plus y squared equals 1, so it's stuck on a cylinder, and the t bit grows as t varies, so you can imagine it's on a cylinder that rises in the z direction, right? So it's doing a spiral, which we call a helix. Now, if I want to find the length of length of one curve, one turn of the helix, so going from, say, 0 to 2 pi, right? I can't do that with my old formula, right? Because that only handles 2D curves. This is the 3D. This is a space curve. It's not going to help, right? But I've got a suitable parameterization. I just differentiate it, right? So the velocity vector here is just derivative of the minus sine t cos t in 1. I find its length. Now, of course, with sines and coses in there, life is good, because sine squared plus cos squared is always 1. Right? So this becomes just the square root of 1 plus 1, square root of 2. And so the length is shockingly easy to calculate. Right? Because you've just got to integrate root 2. Okay? Nice and easy. What about this one? Right? So this curve is called the asteroid. Right? So it's x to the 2/3 plus y to the 2/3 equals 1. Right? Now, if I wanted to do that the old way, so I find the length of one piece of it, which is contained in the second quadrant. So basically, I want the length of the top left piece. You can see by symmetry, all 4 bits have the same length. So if I want the length of the whole thing, I could find a length of one piece and multiply it by 4. That's not what I'm asking, though. Right? But basically, it's this. I want the bit in the top left. It wouldn't matter where I could say top right. It wouldn't make no frickin' difference. Right? Now, if I wanted to do this the old way, it's doable. Let me show you. Basically, we've got the curve. Right? First thing, I need to solve that for y. That's not too bad. It's basically but this is the first alarm bell. We're going to have to integrate this crap. Ooh. Right? It could get nasty. Right? But let's see what happens. I need its derivative. So I get, let's do this carefully. Again, if you don't have to do the chain rule in your head, right? If you don't want, hopefully I haven't stuffed that up. What's this? So this is minus. No, not looking too bad. Now, I need to plug it into my old formula. I need that. So what do we get here? So that all squared, that's x to the minus 2/3. Yep, that goes, that gets 1 plus. Don't laugh at my working out murmuring. Minus 1. Ooh. Oh, that's nice. Note that hardly ever happens, right? But it has happened in this case. So I need the square root. Right, then I know that my length is, now I want the top left of this thing, so x goes from -1 to 0. This integral of this. Now, so this becomes that. All right. Now, here's the funny thing. If you ask, remember I keep saying, you might often wonder, well, I've shown you this program Maple several times, haven't I? And done things with it, and you might, we always get that, let's call them annoying student, It says, well, if a computer can do it all for me, why the hell do I have to do this crap by hand? Right? Because these things aren't smart. Right? And this is a classic example of showing this. Right? Now, this isn't because this is a dodgy ass program. This is actually, everyone's heard of Mathematica, yeah? Everyone knows what Mathematica is? Yeah? Well, this is Mathematica's competitor. They're very, very similar. This one's better though. Right? Well, for me, for what I do, this is better. Now, if I ask this to integrate this function, x to the minus a third, and I want to integrate that from minus 1 what the hell? I'm looking at a picture of this thing. The length can't be a complex number. Right? And that's because Maple is not smart. Right? It's well designed, but it's following a set of rules, and rules like this you can't program. Right? And the reason it's stuffing this up, this is wrong. Right? This is actually completely wrong. Right? This is an error. But it can't be fixed because you can't explain to it what you're actually doing. When you have fractional powers, you should do them by hand. Right? So this is telling me that's its length, which is bollocks. Right? And the reason is because when you get down to here, so 3 on 2 times 0 minus 3 on 2 times... Maple's struggling because when you ask it what is the minus 1 to the power of 2/3, it doesn't understand what you mean. Right? Do you mean in complex terms, as in what is the... That's asking what is the square root of the cube root of 1? Right? Which is what Maple's doing, which is stupid. Right? Unless you're doing complex, you wouldn't do that. Right? The way we would do it by hand, very straightforward. You think of this as the cube root of minus 1 squared, which is, of course, 1, isn't it? Now, I've got a negative length. No, all that means is I've stuffed up taking a sign somewhere, right? All that means is, well, when I solved this for y, I should have been more careful, right? Because you are technically taking a square root. You cube both sides first, then you take the square root. So technically that's plus minus, yes? Right? So all the fact that I got minus 3 on 2, I just took the wrong one. Don't worry about that negative. It's 3 on 2 is the answer I'm looking for. Right? Now you could do it that way. Right? Few issues. Right? You've got to solve it for y. You've got to hope this works. Now this one does because I designed it that way. Right? But it doesn't always work. Right? And then there was this extra complication down here. Right? And then you fire up a computer algebra system and, I might just quickly check my answer. It's stuff doing this by hand, and it gives you that rubbish. Right? But this all hinged on all of this working. Right? Now, if I wanted to do this parametrically, that's going to be easier, and you should get the same answer. Right? Now, how would I do this parametrically? Well, I've got to come up with a suitable parameterization. Can I imagine that as something squared plus something all squared equals 1? Should be obvious that yes, you can. Think of it as x to the third all squared plus y to the third all squared equals 1. Right? So let x to the third be cos and y to the third be sine. I've chosen them that way because I wanted to start at x equals minus 1, y equals 0. No, I don't. Right? I'm going to do this from pi on 2. It doesn't matter. Right? Remember, it's not unique. Right? I've let x be cos cubed, y be sine cubed. Right? But if I want this piece, that means t has to go from pi on 2 to pi, doesn't it? Right? Because the way I've designed it, the t starting here, right? Where t starts at x equals 0, y equals 1, right? And goes anti-clockwise. Remember, always anti-clockwise. So I just want it to go from pi on 2 to pi. Notice in that one, I basically did it from there to there, because the direction you choose should make no difference. Right? It should work out in the long run. Right? That's a suitable parameterisation. Now the first thing is, well, now you've got cos cubes and sine cubes. Oh, this isn't going to work. Right? But let's see. I need its derivative. Right? A bit tricky to do, not too bad. Quick chain rules. I need its length. Remember, when there are trig functions in there, something will almost always simplify with sine squared plus cos squared equals 1. This initially looks terrible, but isn't too bad. I took the negative square root because I know what's going to happen. Right? Because I'm integrating from pi on 2 to pi, between pi on 2 and pi, I'm in quadrant 2, I know sine is positive, cos is negative. Right? So that's a negative times a negative times it's positive. Just if you forgot the minus 3, what would happen is what we did here. You just forget it. Right? You just worry about it later. Right? And then you do the integral, and of course you get the same answer. Totally different intermediate steps, but of course the final answer is the same. Okay? Right, but the whole point is that parametric will in general make life easier. You just got to you make the parameterisation work, and a lot of the time it hinges on the fundamental trig property sine squared plus cos squared is 1. Okay? All right, please do have a work through those examples. Also, don't forget that with the test this week, I have consultation tomorrow from 9 till 12, and the UWA Math Union's got their study night tomorrow night from 4 till 6 in the Reed Library, okay? All right, other than that, I'll see you all on Thursday.